Finally, we're going to wrap up this lecture going over some specialized clearance equations and definitions. We're now going to talk about osmolar clearance. So osmolar clearance is the total clearance of solutes from the blood, and it can be expressed as osmolar clearance. So usually when we talk about clearance, clearance equals U times V over P. And whenever we are looking at a specific factor, let's say we're going to look at the clearance of sodium, we take clearance of sodium equals the urine concentration of sodium times the urine flow rate divided by the plasma concentration of sodium. But let's say we want to look at all the solutes, not just sodium. Well, in that case, you have to take the clearance of all solutes that contribute to osmolality. So the clearance of all solutes equals the urine osmolality times urine flow rate over plasma osmolality. And so as a result, we can calculate the clearance of osmoles, the clearance of solutes from the blood. So that's what this box with the red dots around it is indicating. And here we have an example. So let's say we have a urine osmolality equals 600 milliosmol per liter. We have a urine flow rate of 1 ml per minute. And we have the plasma osmolality equals 300 milliosmol per liter. Well, you plug these values into this equation and you get this second equation in the middle. And we can do some unit elimination as well. So 600 times 1 is 600, okay, divided by 300. So 300 on the bottom, but our units are going to cancel out. That milliosmol cancels with that milliosmol. This liter cancels with this liter, so we're left with mils per minute. So 600 divided by 300 is 2 mils per minute. So pretty much the same as any other clearance equation, but now we can look at the osmolar clearance. And this becomes an important concept because using osmolar clearance, we can calculate free water clearance. The first special clearance equation we're going to go over is called free water clearance. So by definition, this is the difference between water excretion, which would utilize the urine flow rate to determine, and the osmolar clearance. So essentially, it's the rate at which the body excretes solute-free water. So let's take a moment and think about urine. In urine, let's see, we have a little bowl here. In urine, we have some fluid and we have solutes. Okay, so this is what this is representing. Whenever we calculate the free water, whenever we calculate clearance in general, we're calculating the clearance of either something or all of this. Free water clearance, the difference is you're going to calculate only the water. So if you were to separate this out into the content, you have water and then you have solutes. So you see how I've split these apart. Well, you can calculate the clearance of any one thing. Usually we calculate the clearance of things like sodium or creatinine, or not creatine, creatinine, N-I-N-E. But we can also calculate the clearance of just water, and this is free water, meaning water without any solutes in it. And we do so by using the clearance calculation formula as a base. So the clearance calculation formula is U times V over P. But free water clearance is the difference, or the subtraction, between water excretion, or the urine flow rate, which is what this is. V is urine flow rate, So the difference between that and osmolar clearance. And that's why we have clearance of osmoles. So this is all of the solutes that contribute to urine osmolality. So if you know the clearance equation for clearance of solutes, of osmoles, you essentially just take this equation, but you're going to look specifically at the osmoles of all of these things and plug this part of the equation into this. And so that's why we have free water clearance equals V, but this is V with a dot over it, okay? That's urine flow rate minus U osmol minus urine flow rate divided by P osmol, okay? Now, in general, we can say that if you get a negative number as a result, then excess solutes are removed and you're in a state of water conservation. If you have a positive number, water is being excreted, you're forming a dilute urine, and you're in a state of water excess. So let's think about this. If your C of H2O equals a number, so your urine flow rate, and I'm just going to make up some numbers here. Your urine flow rate is 5, and then your clearance of osmoles are 3. Well, that's a positive 2. Okay, so that would mean that you have more water coming out than you have solutes. Okay, so that's why you are in a dilute urine state. Now let's hypothetically change this to 5 minus 15. Well, that's a negative 10. So in this case, you have more solutes coming out than water, so you get a negative number. So that's a concentrated urine. Okay, so for the most part, you can tell just at a glance if your free water clearance is negative, then you are diluting lots of pale yellow dilute urine. If you have, if you have a negative free water clearance, that is a negative, that's a concentrated urine, my apologies. If you have a positive free water clearance, that is a very dilute, kind of pale. And finally, we're going to talk about obligatory urine volume. So what is obligatory urine volume? Well, it is the amount of urine you have to excrete to get rid of all of the excess solutes and waste that your body produces. If you don't excrete them, it will build up in your body over time. That's going to change the tonicity of everything and would be fatal eventually if you do not excrete your excess solutes, waste, metabolic products, and sources of acid. Okay, so we have this concept called obligatory urine volume. So that's the minimum amount of urine and that's a terrible urine, that it takes to account and excrete all of those waste products. And the minimum amount of urine is directly correlated with how much urine you're able to concentrate. So if you can really, really, really concentrate your urine, if you have a very high urine concentration, that means that in, let's say, half a liter of urine, you can put in 2,000 milliosmoles of solute. But if you have an inability to really concentrate your urine compared to, say, other mammals on the planet, if you have low ability to concentrate your urine solutes, then it might take 3 liters of urine to get rid of the same 2,000 milliosmoles of solute. So obligatory urine volume is directly involved with how much can you maximally concentrate your urine. So we can calculate this, and this is calculated by the division of the minimum amounts of solutes you have to excrete per day. So this is essentially the minimum amount of waste product that you have to get rid of in a given day to stay alive. And it's divided by how much you can concentrate your urine. Now, us human beings have pretty standard numbers for this. The minimum solutes you have to get rid of per day as a human being is about 600 milliosmoles per day. So in order to stay alive, you have to continue to get rid of these about 600 per day. But as human beings, our loops of Henle are only deep enough and long enough to create a interstitial fluid hyperosmotic gradient that maxes out at 1200 milliosmoles per liter. So our obligatory urine volume is 600 divided by 1200, and you can cancel the milliosmol units, and you end up with half a liter a day. So to stay alive, a human has to be able to urinate out at least half a liter a day that has a concentration of 600 milliosmoles per liter. So in this is what we need to do to stay alive. Okay. So interestingly, as I mentioned, there are other animals on this planet who can maximally concentrate their urine at amounts that just are staggering. And this little guy up here in the corner, this is a mouse that comes from the deserts of Australia. And this mouse has the ability to concentrate its urine up to 10,000 milliosmoles per liter. This is the highest amount on the planet that we know of. And that is because their loops of Henle, proportional to their kidney, is 10 times greater than what the human loop of Henle is. Obviously, they're a mouse, so their little kidneys are, pretty little. But for their loops of Henle, compared to the size of their kidneys, they are enormous. So they can concentrate their urine up to 10,000 milliosmoles per liter. Fascinating. Okay, obligatory urine volume is also the reason why we get dehydrated from drinking seawater. I've always been fascinated by this concept. It's kind of a hypothetical situation you can bring up, you talk about as kids or something, and it's like if you're stuck at sea in a life raft, why can't you drink the water? You are surrounded by water. Why would you get dehydrated and potentially die if you drink the seawater? Well, it has to do with obligatory urine volume and the fact that humans can max out their urine concentration at 1200 milliosmoles per liter. So let's think about this, okay? If our minimum solute excretion per day is 600 milliosmoles per liter, and we drink 1 liter of seawater, let's say we drink 1 liter of seawater. That 1 liter of seawater is so concentrated, it has about 1200 milliosmoles per liter concentration. So 600 of just our natural body waste products, plus we just ingested a liter of seawater that has another 1200 milliosmoles in it. That's 1800 milliosmoles per liter just in your body and from the seawater. But we can only concentrate our urine up to 1200 milliosmoles per liter. So what's 1800 divided by 1200? Well, that's about 1.5 liters. Meaning, in order to excrete the minimum amount of just waste products that you need to stay alive, plus all the solutes that you drank in that liter of seawater, you have to urinate out 1.5 liters. Okay, but you only drank 1 liter of seawater, but yet you're going to urinate out 1.5 liters. Where does that extra half liter come from? Well, it's coming from your own body. It's coming from your own cells, from your fluids, from your brain, from your intracellular compartments. It's coming from your body. So the more liters of seawater you drink, the more you dehydrate yourself, because you have to eliminate all of that just to stay alive. So I think that's really interesting. Okay, next we're going to go over some very basic definitions, and then we will be done. The first one is diuresis. Definition of diuresis, technically, from physiologic standpoint, is that you are continuously reabsorbing solutes or reabsorbed, but no water is reabsorbed. Meaning, where is all of your water going? Well, water, if it's not being reabsorbed, is just going to go to the bladder. So in this case, you would have a high volume, very watery, dilute urine. Why is it dilute? Well, because you're reabsorbing solutes. Why is it high volume? Well, because your bladder is filling up with water. And in the state of diuresis, your interstitial fluid in the inner medullary area is very low. So remember that bottom of the loop of Henle in humans maxes out at 1200 milliosmoles per liter. Well, here in a state of diuresis, the interstitial fluid concentration is 600 milliosmol per liter. Antidiuresis is the exact opposite, and you need two things for antidiuresis to work. You need ADH, which inserts those aquaporin 2 channels into the principal cells of the collecting duct. And you need high osmolality of the renal interstitial fluid. Okay, so let's look at this together. If you have a high osmolality of the renal interstitial fluid at around 1200 milliosmoles per liter, and you're in the presence of ADH, a couple of things can happen. If you're in the presence of ADH, water is getting pulled out of the collecting duct. Okay, so this is going to be water, water, water. The farther down in the collecting duct you go, the stuff that stays behind gets more and more and more concentrated. Okay, stuff that stays behind gets more concentrated until you get to the point that urea, for instance, is one of those things that contributes to the interstitial fluid hyperosmotic state. Urea passively moves down its concentration gradient from the collecting duct into the interstitial fluid, and it will help drive up that hyperosmotic medullary area to its maximum of 1200 milliosmoles per liter. Furthermore, this is going to kick into the not only urea recycling, where your urea gets picked back up by the loop of Henle and circulates back around and does it again to help maintain that very high osmotic gradient. Meanwhile, you also get sodium chloride being reabsorbed from the thick ascending limb, and you have water that is coming out of the thin descending limb. And this is going to kick in the countercurrent exchanger and countercurrent multiplier mechanisms until we get to the point that we get a salty medulla. Okay, so the saltier the medulla, the more concentrated our urine is going to be.